Okay, let's talk about some unusual observations and how we can detect them. So, the first way to think about unusual observations is via something known as leverage. So, leverage is the amount of influence an observation has on the estimate of beta hat. And so, mathematically, we can define this as the diagonal elements of the hat matrix, and I'll show you in a second why that kind of makes sense as something to do. But just as a reminder, what is that hat matrix? It is X times X transpose X inverse X transpose. We call this the hat matrix because when you multiply it by Y, you get Y hat. So it puts the hat on Y. I think we've been doing a lot with the hat matrix, so hopefully this is very familiar to you now. But what we're going to do is we're going to take the diagonal elements of this hat matrix, and that's going to be the leverage. So this is how you would write this mathematically. We'll call our leverage HI, and that's going to be equal to, if you have big H as our hat matrix, it'll be the ith observation in that matrix, and so that's going to be just along that diagonal. And so, of course, we could write this with the H or the hat matrix fully written out, and we're taking the diagonal of that. So if we were getting the leverage for the first observation, this would be the first element of the diagonal of the hat matrix. If it was the second observation, the second element of the diagonal of the hat matrix, and so on. So why do we use the diagonal of the hat matrix for this? Well, if you remember the variance of the residuals, we talked about this, I think, in the last class, but the variance of the residuals, for a residual for observation I, the variance is going to be sigma squared times 1 minus hi. So hi is this exact leverage, and again, it's that diagonal of the hat matrix. And so if you have large leverage points, if this hi is big as it gets closer to 1, it's going to pull that fit towards yi. Because as this gets bigger, as hi gets bigger, that makes this variance get smaller, because if you have 1 minus something that's big, then it's going to get closer and closer to 0, and so this variance is going to get smaller and smaller. So the leverage, hi, this is always going to be between 0 and 1. How do we know this? Well, I'm going to show you, and I'm going to use the fact that the hat matrix is idempotent and symmetric. So this is using the facts that you proved earlier in this class. This is why these proofs are important, because we use them kind of over and over again for showing different quantities throughout this class. So we can write this ith element of the hat matrix, or of the diagonal, as the sum over j of hij times hji. And we know, because we know that this is idempotent, then we know that this is going to be equal to hij squared. And we can pull out the ith term from this. So this is we can pull out basically when I equals j. So I'm going to pull that out here into the front. And so I've got hii squared plus, and then the sum of hij squared, where j and I are not equal. So all I've done is I've just pulled out one element from this summation. I've pulled out the time when I is equal to j, and then I've left the remaining ones there. And so this here, hii, that's exactly our hi. So that's the same thing. Hii just denotes the diagonal, the ith diagonal of the hat matrix. And so I can write that as hi. So I'm just replacing this hii with hi squared here. So this hii squared now is little hi squared. These are just exactly equal. They mean the same thing. Plus, we still have this second term. Okay, so what does that mean? Well, that means that hi must be less than hi squared, because if we have hi has to be, or rather, I'm sorry, hi has to be greater than hi squared. And why is hi greater than hi squared? Well, hi is equal to hi squared plus the summation of other somethings that are squared. And so because these are squared, we know that this summation is going to be positive. And so hi is equal to hi squared plus something positive. And so that means that hi must be larger, must be greater than hi squared. And so when is a number going to be greater than itself squared? Well, that's going to be only when it's between 0 and 1. And so this implies that HI must be between 0 and 1. So we know that these leverage points are going to be between 0 and 1. And going back to this variance, that can sort of, if we know that if it's 0, then the variance of that residual is going to be equal to sigma squared. And we know if it's 1, then that variance of the residual is going to essentially be 0. And so that kind of gives us some sense for why this is a sensible thing to do. All right, so remember that the sum of the diagonal of the hat matrix, or the sum of these HIs, that's equal to P plus 1. And you know this, you proved this because you showed that the trace of the hat matrix was equal to P plus 1. And when you sum up the diagonal elements, that's the same thing as taking the trace. And so what this means is that the average value for HI is going to be P plus 1 over N. And so we can use that average value to kind of give us a sense for where kind of a cutoff might be for what we might expect. And so a rule of thumb for leverages, a greater than 2 times P plus 1 over N should basically get an extra look. So if you're essentially 2 times what the expected average would be for these leverage points, then maybe you should get an extra look. And so we can use this to kind of just be a rule of thumb. All of the methods that I'm going to be talking about today, they're ways to identify points that are either leverage points or outliers or influential points, and we're going to talk about those other two in just a minute. But all of the rules of thumb that I'm using, they do not mean that you necessarily need to throw out these data points or anything. They just give you kind of reason to give them an extra look. And the reason you want to give an extra look is because they kind of give you some sense that, you know, you might want to decide if the structure of your model is correct. So are you really fitting the model with the appropriate structure? They may help you think about, was this data collected properly? So maybe there were some data entry errors and things like that. Often my first go-to when I see these types of things is I think, maybe my model structure is not quite right. Maybe I need to, add a variable or think about some transformations or something like that. Very, very rarely would I actually throw out a point unless there was kind of very good reason to do so. All right, so standardized residuals. So we can use these leverages to standardize the residuals. And so instead of plotting the residuals, we can plot the standardized residuals, which basically just takes the residual and divides it by sigma hat times the square root of 1 minus HI, which, if you recall from the previous slide, we're basically just, we're dividing by the square root of the variance for the residual, which is kind of a sensible thing to do. And so a rule of thumb is that for those greater than 4, it would be very unusual to have a standardized residual greater than 4, and so maybe those should get an extra look. Okay, so what I want you to do is I want you to use this data that I've given you here, and I want you to calculate the leverage for each observation and determine whether any are unusual, and then I want you to calculate the standardized residuals. So go ahead and take a couple minutes to work on that. I want you to do this by hand. We're going to talk about R functions that can help with this, but I think it's good practice to kind of get this by hand at first.